You think you know what space is. It's the emptiness around you, the distance between objects, the void that exists whether anything fills it or not. It's just there, obvious, simple, the stage on which the universe performs. And time is what clocks measure. It flows forward at a steady rate, second by second, minute by minute, the same for everyone everywhere. It's the river we're all floating down together, unable to stop or reverse course. Past, present, future, they're as real and distinct as up, down, and sideways. This is what your experience tells you. This is what makes sense. This is wrong. Space and time aren't what you think they are. They're not separate. They're not absolute. They're not even necessarily fundamental. Everything you've experienced about them, the feeling that time flows, that space is empty, that there's a universal now that everyone shares, is an illusion created by the specific conditions of your existence. You live on a planet with weak gravity, moving at speeds far slower than light. In this narrow slice of reality, space and time appear simple and intuitive. But venture beyond these conditions, approach the speed of light, enter a strong gravitational field, probe the quantum realm, and space and time reveal themselves to be something far stranger. They're not the stage. They're part of the performance. They can stretch and compress. They can curve and ripple. They can be warped by mass and energy. They might not even exist at the smallest scales. And at the moment of the Big Bang, they didn't exist at all because they hadn't been created yet. This is the story of what space and time actually are, as far as physics can tell us. It's a story that will force you to abandon your intuitions, to accept that reality, at its deepest level, operates nothing like your everyday experience suggests. It's a journey from the comfortable certainty of Newton's absolute space and time, through Einstein's revolutionary fusion of them into spacetime, to the quantum mysteries that suggest space-time itself might be an emergent illusion. By the end, you won't look at the empty air around you the same way. You won't think of time as a simple forward flow. You'll understand that you're not sitting in space watching time pass. You're embedded in a four-dimensional fabric that curves, flexes, and vibrates in ways that determine the very structure of reality. Welcome to space-time, the most fundamental aspect of existence that you've been completely wrong about your entire life. For most of human history, space and time seemed self-evident. Space was the container that held everything. Time was the universal clock that ticked away regardless of what happened within it. This was the framework that Isaac Newton formalized in the 17th century, and it worked brilliantly for describing the motion of objects, the orbits of planets, the behavior of everything humans could observe. Newton's space was absolute. It existed independently of anything within it. You could remove every particle of matter, every photon of light, every field and force, and space would still be there, an infinite three-dimensional grid stretching in all directions, providing the coordinates by which you could describe where things are. In this view, space was like a cosmic graph paper. It had no properties of its own. It didn't bend or stretch. It didn't interact with matter. It simply existed as the backdrop against which physics played out. Newton's time was equally absolute. It flowed at the same rate everywhere, for everyone, always. A second on Earth was a second on Jupiter, a second in the Andromeda Galaxy, a second anywhere in the universe. There was a universal now, a present moment that extended across all of space simultaneously. The past was what had happened. The future was what would happen. And time marched forward uniformly, indifferent to the events occurring within it. This framework is intuitive because it matches your experience. When you look at your surroundings, space appears fixed and unchanging. When you check your watch, time seems to flow steadily. The laws of motion Newton, derived based on this absolute space and time, predicted planetary orbits with stunning accuracy. They worked, but they worked only because humans at the time couldn't test the extreme conditions where the framework breaks down. The cracks started appearing in the 19th century. James Clerk Maxwell unified electricity and magnetism into electromagnetic theory and discovered that light is an electromagnetic wave traveling at a specific speed, about 300,000 kilometers per second. But speed relative to what? If space was absolute, there had to be some reference frame at rest, a cosmic grid against which all motion was measured. Scientists called this the luminiferous ether, an invisible substance, filling space through which light waves propagated, the way sound waves propagate through air. Experiments were conducted to detect Earth's motion through this ether. The most famous was the Michelson-Morley experiment in 1887, which attempted to measure differences in the speed of light depending on Earth's direction of motion. If Earth was moving through a stationary ether, light should travel faster in some directions than others, the way a boat moves faster downstream than upstream. The result shocked everyone. There was no difference. Light traveled at exactly the same speed in all directions, regardless of Earth's motion. It was as if the ether didn't exist, or as if something more fundamental was wrong with the whole framework. The answer came from a patent clerk in Switzerland who was thinking about what it would be like to ride alongside a beam of light. In 1905, Albert Einstein published a paper that destroyed Newton's framework and rebuilt reality from the ground up. It was called On the Electrodynamics of Moving Bodies, but it became known as the theory of special relativity. And it began with two simple postulates that had profound implications. First, the laws of physics are the same in all inertial reference frames. If you're in a train moving at constant velocity, physics works exactly the same as if you're standing still. There's no experiment you can do inside a closed room to determine whether you're moving or stationary. Motion is always relative. Second, the speed of light in vacuum is the same for all observers, regardless of their motion relative to the light source. That second postulate is the one that breaks everything, because if light always travels at the same speed, no matter how you're moving, then space and time can't be absolute. They have to adjust to keep the speed of light constant. Imagine you're on a train platform and a train passes by at high speed. Someone on the train shines a flashlight forward. You, standing on the platform, measure the speed of the light from that flashlight. According to Newton, you should measure the speed of light plus the speed of the train. But you don't. You measure exactly the same speed of light as the person on the train. How is this possible? The only way is if time is running slower on the train from your perspective, and distances along the direction of motion are contracted. Space and time literally adjust themselves to ensure light's speed remains constant. This is time dilation and length contraction predictions that seemed absurd, but have been confirmed by countless experiments. A clock moving relative to you ticks slower than your clock. A ruler moving relative to you is shorter in the direction of motion than an identical ruler at rest. These aren't illusions or measurement errors. Space and time themselves are different for observers in relative motion. But the deeper revelation was this: space and time aren't separate entities. They're unified into a single four-dimensional structure called spacetime. You don't exist in three-dimensional space with time flowing separately. You exist in four-dimensional space-time, moving through it along what's called your world line. Your world line is your path through space-time. Every moment of your existence, past, present, and future, is a point on that line. From the perspective of space-time, your entire life is a fixed structure, a four-dimensional object. The feeling that time flows, and that only the present moment is real, is an artifact of consciousness, not a feature of space-time itself. This was revolutionary, but special relativity had a limitation. It only applied to observers moving at constant velocities, not accelerating, and it didn't include gravity. Einstein spent the next 10 years trying to incorporate acceleration and gravity into the framework. What he discovered was even stranger. In 1915, Einstein completed his general theory of relativity, and it redefined gravity in a way that seemed impossible. Gravity, he said, isn't a force. It's the curvature of space-time itself. Mass and energy warp the fabric of space-time around them. This curvature tells objects how to move. What you experience as the force of gravity pulling you toward Earth is actually you trying to move in a straight line through curved space-time. Earth's mass has curved space-time so severely that the straightest possible path called a geodesic appears to you as falling downward. John Wheeler later summarized it perfectly. Space-time tells matter how to move. Matter tells space-time how to curve. Imagine space-time as a stretched rubber sheet. Place a bowling ball on it, and the sheet curves downward around the ball. Now roll a marble nearby. The marble doesn't follow a straight path. It curves toward the bowling ball, not because the ball is pulling on it with a force, but because the marble is following the curved geometry of the sheet. That's gravity. Earth curves space-time around it. You're following the curved geometry. You feel weight not because Earth is pulling you down with a force, but because the ground is pushing up against your natural motion through curved space-time, preventing you from following your geodesic. This explains something Newton couldn't: why gravitational mass and inertial mass are exactly equal. In Newtonian physics, it's a mysterious coincidence that the mass determining how much gravitational force you experience is identical to the mass determining how much you resist acceleration. In general relativity, there's no mystery. There's only one kind of mass. And gravity isn't a force, so there's no separate gravitational mass concept needed. The predictions of general relativity have been confirmed again and again. Light bends when it passes near massive objects because space-time itself is curved, and light follows the curvature. This was first confirmed during a solar eclipse in 1919, when stars near the sun appeared shifted from their usual positions because the sun's mass curved space-time, bending the starlight. time runs slower in stronger gravitational fields. A clock on the ground floor of a building ticks slower than an identical clock on the top floor because the ground floor is deeper in Earth's gravitational well deeper in curved spacetime. GPS satellites have to account for this effect. Their clocks run faster than clocks on Earth's surface, and if engineers didn't correct for general relativity, GPS would accumulate errors of kilometers per day. Gravitational waves ripples in spacetime itself were predicted by Einstein, but not detected until 2015, a century later. When black holes or neutron stars collide, they send waves through spacetime that stretch and compress space itself as they pass. We've now detected dozens of these waves, each one confirmation that spacetime is a physical thing that can vibrate like a drum. You're not sitting on a planet being held down by a force. You're sitting on a planet that has carved a well in spacetime, and you're resting against the walls of that well. The ground beneath you is constantly accelerating upward through curved spacetime at 9.8 meters per second squared, pushing against your natural geodesic motion. Gravity is geometry, and spacetime is the arena in which that geometry plays out. Perhaps the most unsettling implication of relativity is what it does to time. Not just that time dilates, that's strange enough, but that there is no universal now. The present moment isn't an objective thing that extends across the universe. Simultaneity itself is relative. If you and someone else are at rest relative to each other, you'll agree on whether two distant events happen at the same time. But if you're moving relative to each other, you'll disagree. Events that are simultaneous in one reference frame occur at different times in another. There's no way to say which perspective is correct. Both are equally valid. This means the universe doesn't have a single present moment. There's no cosmic now that sweeps across space, transforming future into present into past. Instead, space-time is a four-dimensional block where past, present, and future all exist equally. What you call now is just your particular slice through that block, and someone moving relative to you takes a different slice. Philosophers call this the block universe or eternalism. If you take relativity seriously, the past hasn't ceased to exist, and the future hasn't yet come into being. They're all there, in space-time as real as the present. The flow of time, the feeling that the present moment is uniquely real, and that time is passing, is an illusion created by consciousness, not a feature of physical reality. This has profound implications. If your entire life exists as a structure in space-time, does that mean your future is already determined? If the moment of your death exists in space-time just as much as the moment you're experiencing now, do you have free will? These are questions physics can't fully answer because they venture into philosophy and consciousness. But the physics is clear. In the framework of relativity, the universe doesn't evolve moment by moment. It simply is a four-dimensional space-time with all events existing timelessly within it. Time dilation adds another layer of strangeness. The closer you move to the speed of light, the more slowly time passes for you relative to a stationary observer. This isn't theoretical. We've confirmed it with atomic clocks on airplanes, with particle accelerators where subatomic particles live longer when moving at high speed, with GPS satellites that must account for both special and general relativistic time dilation to work properly. If you traveled on a spaceship at 99.99% the speed of light for what felt to you like 1 year, then returned to Earth, you'd find that over 70 years had passed on Earth. Your twin sibling would be elderly while you'd aged only a year. This is the famous twin paradox, though it's not really a paradox. It's a straightforward consequence of time dilation. The same effect occurs in strong gravitational fields. Near the event horizon of a black hole, time slows dramatically relative to distant observers. If you could hover just above a black hole's event horizon and watch the universe, you'd see the distant cosmos speed up. Stars would be born and die in what seemed like moments. Galaxies would evolve and collide and fast forward. And if you waited long enough, you'd watch the entire future history of the universe play out. Time isn't a universal flow. It's relative, variable, and tied inextricably to space. And the deeper you look, the more mysterious it becomes. General relativity describes spacetime as smooth, continuous, and infinitely divisible. You can zoom in on any region of space or any duration of time to arbitrary precision. Spacetime is a fabric, a manifold, a geometric structure that curves gracefully in the presence of mass and energy. But quantum mechanics tells a different story. At the smallest scales, the quantum realm is anything but smooth. It's discrete, probabilistic, and fundamentally uncertain. Energy comes in packets called quanta. Particles exist in superposition of states until measured. The Heisenberg uncertainty principle says you can't know both position and momentum with arbitrary precision. There's a fundamental limit to how well you can define these quantities simultaneously. And if quantum mechanics applies to everything which every experiment suggests it does, then it must apply to space-time itself. At small enough scales, space-time cannot be smooth and continuous. It must become quantum discrete, uncertain. This scale is the Planck length, about 10 to 35 meters. It's the smallest distance that has any meaning in physics. The length at which quantum fluctuations of space-time itself become significant. To give you a sense of how small this is, a Planck length is to an atom what an atom is to the observable universe. It's incomprehensibly tiny. At the Planck scale, space-time is believed to undergo quantum fluctuations, constantly roiling and churning in what's called quantum foam. The smooth fabric of relativity breaks down into a froth of quantum uncertainty. Space and time themselves become indistinct, fluctuating wildly, unable to be defined with precision. We've never observed this directly, and we probably never will. The energies required to probe the Planck scale are beyond anything we can produce. The Large Hadron Collider, the most powerful particle accelerator ever built, operates at energies trillions of times too low. Probing the Planck scale would require a particle accelerator the size of the galaxy. But theoretical physicists can calculate what happens at these scales, using the mathematics of quantum field theory and general relativity. And when they try to apply both theories together, the equations break down. They give infinite, nonsensical answers. The two pillars of modern physics, quantum mechanics and general relativity, are fundamentally incompatible at the Planck scale. This is the central crisis in theoretical physics. We have two extraordinarily successful theories that describe different aspects of reality with stunning accuracy. Quantum mechanics governs the behavior of particles and fields. General relativity governs the behavior of space-time and gravity. Both are confirmed by countless experiments, but they can't both be right at the deepest level because they contradict each other. Something is wrong. Either quantum mechanics needs modification at very small scales, or general relativity needs modification, or both do. Or perhaps more radically, space-time itself isn't fundamental. It's emergent, constructed from something deeper that operates according to different rules. This is where things get truly speculative and truly strange. If space-time breaks down at the Planck scale, what replaces it? What is space-time made of? Or is it even fundamental at all? Several competing theories attempt to answer these questions. None have been confirmed by experiment, but each offers a glimpse of what a quantum theory of gravity might look like. String theory proposes that the fundamental constituents of reality aren't particles, but tiny vibrating strings of energy. Different vibrational modes of these strings correspond to different particles' electrons, quarks, photons, and even gravitons, the hypothetical particles that carry gravitational force. In string theory, space-time emerges from the interactions of these strings. Space and time aren't fundamental. They're derived properties of a deeper stringy reality. The theory requires extra dimensions beyond the 4 we experience, typically 10 or 11 dimensions, with the extra ones curled up at scales too small to observe. Loop quantum gravity takes a different approach. It attempts to quantize space-time itself without invoking strings. In this framework, space is not continuous, but discrete, built from tiny loops of quantum geometry. These loops weave together to form a structure called a spin network, which evolves over time to form a spin foam. Space has a smallest possible unit roughly, the Planck length, and time proceeds in discrete ticks, not smoothly. Space-time is fundamentally granular, like pixels on a screen. The holographic principle offers an even more radical suggestion. It proposes that all the information contained in a volume of space can be encoded on the boundary of that volume, like a hologram. This idea comes from the study of black holes, where Stephen Hawking and others discovered that a black hole's entropy, its information content, is proportional to the area of its event horizon, not its volume. If this holds for the universe at large, it suggests space-time itself might be a holographic projection of information encoded on a distant two-dimensional surface. Some physicists, inspired by this, suggest space-time as emergent, not fundamental, but constructed from something more basic, perhaps information or quantum entanglement. Just as temperature emerges from the average motion of molecules, space-time might emerge from the entanglement structure of quantum bits of information. In this view, asking what space-time is made of is like asking what temperature is made of. It's the wrong question. Space-time is a collective property that emerges at large scales from quantum relationships at small scales. None of these theories is complete. None has made predictions we can test with current technology. We're in a strange position. We know general relativity and quantum mechanics are both correct within their domains. We know they conflict at the Planck scale, and we have several mathematically beautiful proposals for resolving the conflict, but no way to determine which, if any, is right. What we can say is this: space-time, as you experience it, is almost certainly not the deepest level of reality. It's an approximation, valid at the scales and energies of everyday life, but breaking down under extreme conditions. The true nature of space and time remains one of the greatest unsolved mysteries in physics. Even if we discover a quantum theory of gravity, even if we figure out what space-time is made of or whether it's emergent, one question remains. Why does space-time exist at all? At the Big Bang, space-time itself came into being. There was no before in the conventional sense, because time began at that moment. Asking what caused the Big Bang or what existed before it assumes time already existed, which it didn't. The question may be meaningless, like asking what's north of the North Pole, but perhaps there's a deeper framework, something that exists independently of time and space from which space-time emerges. Some theories suggest a quantum vacuum, a state of pure potential where virtual particles and fields fluctuate in and out of existence. In this view, our universe is one possible configuration that crystallized out of the vacuum, with space-time as a property of that configuration. The multiverse hypothesis proposes that our space-time is one of countless bubble universes, each with its own space-time structure, its own physical laws, its own dimensionality. These universes might be causally disconnected, unable to interact or communicate, each existing in its own separate space-time framework. Or perhaps, as some interpretations of quantum mechanics suggest, space-time is intimately tied to consciousness and observation. The measurement problem in quantum mechanics, the question of why quantum systems seem to collapse into definite states when observed, might hint that consciousness plays a role in constructing reality. This is speculative and controversial, but it raises the possibility that space-time, like the quantum wave function, is partially dependent on observation. The truth is, we don't know, and we may never know fully. Some questions might be beyond the reach of science, not because we lack intelligence or technology, but because they require a perspective outside our universe, outside our space-time, which may be impossible. But that doesn't stop us from asking. It doesn't diminish the value of pushing as far as we can, uncovering layer after layer of deeper truth. Every question answered reveals new mysteries. Every experiment completed raises new puzzles. Space-time might be fundamental. It might be emergent. It might be a projection, a hologram, a collective property of quantum entanglement. It might not be the right question to ask at all. What we do know is that space-time is stranger, more flexible, more intimately connected to matter and energy, and more mysterious than any human before the 20th century imagined. The empty air around you isn't empty. The space between stars isn't mere absence, and time isn't a river carrying you forward. You're embedded in a four-dimensional structure that can curve, stretch, ripple, and possibly dissolve into quantum foam at the smallest scales. You're not watching the universe from outside. You're part of its fabric. Right now, you are moving through space-time at the speed of light, not through space-time. Every object, no matter how still it appears, travels through space-time at exactly the speed of light. The difference is how that motion is divided between the spatial dimensions and the time dimension. When you're at rest in space, all your motion through space-time is in the time direction. You're moving through time at maximum rate. When you move through space, some of that motion gets redirected from the time dimension into spatial dimensions. The faster you move through space, the slower you move through time, until at the speed of light, all your motion is through space and none through time, which is why photons don't experience time at all. You're not sitting still. You're hurtling through the time dimension at 299,792,458 meters per second, the speed of light. That's what it means to exist. The spacetime you're embedded in was created 13.8 billion years ago in the Big Bang. It's been expanding ever since, carrying galaxies apart, stretching like a balloon inflating. The space between distant galaxies grows not because they're moving through space, but because space itself is growing. Massive objects like stars and black holes curve this space-time, creating wells of gravity that trap planets in orbits and bend light rays. When gravitational waves pass by ripples from colliding black holes billions of light years away, they stretch and compress the space-time you occupy, changing the distance between objects by fractions of an atomic diameter. At quantum scales, the space-time you trust to be smooth and continuous dissolves into probabilistic chaos. And at the deepest level, space-time might not be fundamental at all. It might be an emergent property, a collective phenomenon arising from something more basic that we haven't yet discovered. You've been wrong about space and time your entire life, but not because you're stupid or unobservant. You're wrong because your evolution occurred in a narrow regime, weak gravity, low speeds, where space-time appears simple. It's like fish in the ocean who've never experienced ice or steam. They know water, but they don't know it can be solid or gaseous. They lack the experience to intuit its full nature. Humans lacked the experience to intuit the full nature of space-time until we built instruments sensitive enough and theories powerful enough to probe beyond everyday conditions. And what we found is that reality is far stranger than common sense suggests. Space and time are not the stage on which the universe performs. They're part of the show, dynamic and responsive, curved by matter, linked indissolubly, possibly emergent from deeper principles. They're not what you think they are, but now you know. And you can never look at the space around you or the time you're moving through the same way again. You're not in the universe. You're a pattern in space-time, a temporary configuration of matter and energy, moving along your world line from birth to death, embedded in a four-dimensional structure that curves and flexes in response to everything within it. This is what space and time actually are, or at least it's as close as physics has brought us. The deeper truth, if there is one, awaits.